Alright, so starting with this episode, we're going to talk about mitigating specific attack types. And we're probably going to have multiple videos about this because there's just so many types of attacks out there. You cannot imagine how creative the attackers can be. But you will have a pretty good idea after we're done with this chapter. And we're going to start with what I like to call the classics. And the first one here is buffer overflows. So what exactly is a buffer overflow? Well, let's take it easy and think about what exactly is a buffer. Well, a buffer is just a place in memory where you decide at some point to store some data. You just pre-allocate it and say, this is where I will store whatever you send me. Your username, your profile picture, your comment on a website, anything that can be received from a user is going to be stored in an input buffer. Secondly, right, what's an overflow? Well, you can probably imagine what's an overflow, right? Well, that's exactly what you think about when you talk about, I don't know, overflowing your sink, your bathtub, your beer glass. It's basically what happens when you try to store more than the recipient can handle. Well, when talking about buffers, we're basically trying to store more data than the buffer can handle. Right now, the question could be, well, so what? Okay, I'm trying to write more data than the buffer allows me to, and then you might think that, all right, I'm gonna receive some error from the program, and that's it. I can try again. I can just ignore it, right? Life moves on. Why do we care about this? Why do we care about buffer overflows, and what does this have to do with cybersecurity? The way that you're thinking right now is pretty much okay. The problem is that you're not gonna be getting that error every single time. So the question becomes, what happens after a buffer overflow? And the answer is, unfortunately, we don't know, right? It depends on a number of factors, and it depends on whether the overflow was accidental or was intentional. So in order to understand what all the possible effects, the possible outcomes of a buffer overflow can be, we need to take one step back and look at the big picture here. And start by looking at how a program sees its memory when it first starts up. Alright, so this right here is just a slightly simplified representation of how a program sees its memory as it is allocated by the operating system right after that program starts. And the memory is a linear space, which means that every position in this memory space has a specific address. And in our example here, we start from a theoretical 0 address here at the bottom, up to a maximum theoretical value right here at the top. Now the real values of course are much higher than this because we need to address a large amount of memory nowadays, but generally we will be using hexadecimal digits, just the one that you see here, to represent memory addresses for two reasons. First of all, because they allow us to write addresses using less characters, and also because the hexadecimal system allows us to use 2 hex digits to represent 1 byte. And that's actually because each hexadecimal digit ranges from 0 to 9, followed by A through F. So with 2 digits, we're going to end up with 16 times 16, which is 256. That's the maximum value of a byte. Because a byte is 8 bits, 2 to the power of 8 is 256. Right, now coming back here, let's see what all these memory regions are. And we're going to start with the least interesting ones, like the text area. Now the text here is going to store the actual program code. Those are the actual program instructions, and most of the time they're going to be read-only, so we don't really care about those because we cannot change those. At the top, we have the kernel area, which is not the operating system's kernel, but we are going to find in here stuff like the arguments that we use to launch the program, and also some environment variables that the program might use. Then the data area stores variables. Initialized variables, uninitialized variables, doesn't matter, they're all here. Then we have the heap. Now the heap stores what I like to call the big stuff. That is, files that you load in memory, the document that you're currently editing in Word, for example, or the level that you're currently playing in a game. Anything that's not a variable or a simple data structure and needs to be loaded into memory and takes up a lot of space is going to be stored here in the heap. And we're also going to find the global variables here as well. And we left the stack at the very end because this is where things get interesting. We're going to talk about the stack in just 1 second. Now, before discussing about the stack, there's one more thing here that you should know. You've probably noticed that we have a big unpopulated area here in the middle. So what's this? What's this area? Now this data structure is by default empty, but we have two memory areas that are constantly competing for it from two different sides. And as you can guess, just by looking at this picture, the first one here is going to be the stack, and the second one is going to be the heap. And that's because both the stack and the heap can grow when needed, and they will start taking up space from this empty area in the middle. Now the heap is going to grow, of course, whenever you need more memory to load more stuff into it, like another document, another PDF file, another level. Now, in order to understand how the stack grows and what exactly does a stack do, let's have a look at a very short piece of code. Now, don't freak out. This is a very simple C program right here, which doesn't do much, actually doesn't do anything, but you don't need to know C programming for the CySA Plus exam, but we need a very simple example like this just to exemplify and show you what happens when a buffer overflow occurs. Now, this simple program here, like any other program, is going to start its execution with the main function. That's going to be the first function to be executed. And the first instruction on line 10 is going to be a call to the myCopy function. Now, the myCopy function also receives an argument. This argv that you see right here is going to be the first argument that I provide to the program when I launch it. For example, if my program is called hello, right, and I write in the command line hello Andrew, then Andrew is going to be that first argument that gets passed to the myCopy function. And well, when the program execution sees this function call right here on line 10, the program is basically going to jump its execution right here. So it's going to start executing instructions one by one from this function right here until it reaches the end of the function, and then the execution comes back to the following instruction in my main program, just like you would expect whenever you call a function in any programming language. Now, this type of execution here is going to involve the stack. So before the program starts executing the myCopy function, it's going to store the following things on the stack. First, it's going to extend the stack to make room to store the arguments of the myCopy function, in this case, the name parameter. And it's going to store it right here. All right, next thing that ends up in the stack is going to be another place allocated to store the return address for this function. Now, why do we need a return address? Before the program needs to remember somehow to put a bookmark to the place where it previously was before it started executing this function. Think of this just like the bookmark that you would use when you're reading a book and you want to perhaps peek a few pages ahead or just look at the table of contents. You just use a finger or a paper bookmark just to mark the current page, and then you look back or forward into some other location in that book, right? When you're done checking that outside info, you know exactly at what page you need to go back to where you were before you digressed and accessed some other data. Now, that's exactly what happens with functions as well. The program execution actually left the main function to head over and execute the myCopy function. So when myCopy is done, the program needs to know where it's supposed to come back to. In our case here would be line number 11, which is actually the end of the main function as well. But that doesn't matter, right? It could be any other additional instruction present in the main function. So the return address is going to be a memory address that points to the next line to be executed in your main program. And one more thing, we're going to also store on the stack. We're going to allocate more memory here, and we're going to store any local variables or any variables that represent the current context of our function. So in this case, our buffer of 10 positions, our character buffer of 10 characters here, is also going to be stored right here on the stack. Now, of course, when we're done executing the myCopy function, all this information here is freed, and the stack comes back to its initial size. Now, a couple of weird things about the stack behavior. First, you can see that the stack kind of grows downwards. And it's just a bit weird the way it's implemented in operating systems, because it actually grows from higher memory values towards lower memory values. And that's just the way things are. All right, so that's one weird thing about the stack. Now, another one is that by definition, the stack is a data structure that behaves just like let's say a stack of plates, right? Let me see if I can draw a couple of plates here. Just imagine that these are plates. And the idea of a stack is that you can only access the topmost element in that stack, the one right here. And we actually have a couple of operations, and the most important ones are the operation of putting something on the stack, and this one is called a push. Another operation is removing something from a stack, which is called a pop. And as you can see, we can only work with the topmost element. And of course, there is another type of operation here, which is called peek, which allows us to just read the first element without removing it. But the main idea here is that in a stack data structure, which is a very widely implemented data structure in programming, you can only access the topmost element at any single time. So in our case here, our topmost element would basically be our local variables. That would be our buffer. Now let's go back to the code for just a second here and look at what this myCopy function actually does. You can see it allocates a buffer right here, which we've seen that it ends up on the stack, and then we have a simple function call. Another function, this one is built in into the standard library of C or C++, and what it does is actually copies one string into another, a string of characters into another. And this string copy here is considered to be an unsafe function because it receives only two parameters. First one is the buffer, that's the destination. Where do we want to copy that content to? And then the name, which is actually the variable that you see the function receives right here at the top as an argument, that's the source of the data. So basically what this function does is reads the contents in this string of characters called name until it reaches a zero value, a null terminating value, and then puts its contents into this buffer, which is pre-allocated right here. Now, of course, if name here is less than the 10 characters that we've allocated for this buffer, everything would be just fine, right? We don't have any overflow happening here. The buffer can hold as much data as we give it, and inside of the stack, things would probably look something like this. Now, assuming that the argument that we've launched this program with is something like Andrew, then this string Andrew right here is going to end up in this allocated space inside of the stack. And another weird thing, another weird behavior of the stack is that even though it grows from high values to low values, well, the way memory actually gets allocated is from low values to high values. So what we're going to do here is actually not store Andrew like this, but instead we're going to store it in reverse order so that we can go from lower values to higher values. So we're going to basically write it from right to left, kind of like this. This word right here. Now remember, this buffer only has 10 positions, so we can only store at most 10 characters in here. So what happens if Andrew suddenly becomes Andrew 1, 2, 3, 4, just like this? Well, it's going to end up in the stack as 4321 word now. Okay, we still have a valid buffer here. But what happens if Andrew 1, 2, 3, 4 actually becomes Andrew 1, 2, 3, 4, 5, 6, 7, 8, 9, 0? What happens with this string when we try to give it to the string copy function? Well, remember when I said that the string copy function right here is considered to be unsafe? Well, that's simply because, as you can see, it receives two arguments. The one is the destination and the one is the source. But there's no argument saying how much should I copy from the source to make sure that I'm not going to overflow the buffer in the destination. And if you think about the fact that, well, the program is going to take care of this, the operating system is going to take care of this. I mean, the operating system sees that I only have 10 values here. How could it attempt to write beyond those values? Well, that's another discussion here, but actually the buff and name parameters that we have in here don't contain the entire string, pre-allocated string. These are just pointers to the beginning of the string. So basically the string copy here, what it does, it says start copying from the name location to the buffer location as long as you find something in the name location. There's no stopping it, right? There's nothing to tell it to stop after 10 characters. And this is where we're going to cause a buffer overflow. Now, a buffer overflow like this is going to happen in the stack, is going to occur in the stack in a very nasty way. That's because the space that we just allocated in the stack for this buffer has depleted. So there's no way for me to keep adding here 5 and 6 and 7 and so on. No, what's going to happen is it's going to continue writing onto the next available address inside of the stack. And which one is the next available address? Well, this field right here, the return address. And it's going to start overwriting the return address with the rest of the content that I've provided inside of my buffer. Now, what's going to happen now? The problem is that whenever the myCopy function finishes execution, the program is going to try to read this return address right here to figure out where to jump its execution. Ideally, this was supposed to hold line number 11 in our code. Right now, I've just overwritten it with some arbitrary values. Now, in most situations, if this happens accidentally, this is going to end up as a segmentation fault. So that's going to be an error which is going to crash your program, because there's probably not going to be a valid address like this for the program to jump to. But imagine that you are an attacker. If you are an attacker, then you can actually craft the contents of this buffer right here to make sure that the end of it includes the exact return address that you want your program to read whenever it exits its current function. Now you're basically telling the program through a buffer overflow, go ahead and execute some other piece of code, some other type of code that I've provided you. And that's a very dangerous type of attack, because you're basically interfering with the normal program execution. You're telling it, just ignore your normal code, start executing my code. And this is how you take control of a remote system. You can tell that system, well, instead of executing your own functions, execute a reverse shell for me, or execute a denial of service attack for me, or execute anything on my behalf, which means that I currently have access to that machine, I can control that machine, and that machine has been breached and is under the attacker's control. Complicated stuff, I know, but it happens, and it's actually the most common type of exploit. Unchecked boundaries, unchecked buffers that can be overflown can be easily hacked using examples very similar to the one that I've just given you here, so that a potential attacker can just send a valid request, can be over HTTP, over the network. Sometimes it can even be an email or just a file that you trick someone into opening it. And all that file is going to provide an input that's going to overflow a certain buffer, which the attacker knows that is going to allow him or her to overwrite a return address and to cause that program to jump its execution to some different piece of code provided by the attacker. Now, most likely that additional piece of code, that malware code that you convince the program to execute instead of its own code, is also going to be provided through that buffer overflow as well. So the attacker can actually do something like this. I mean, you don't even need to jump that far. You can just take this crafted jump address right here and tell it, jump maybe a couple of positions downstairs in the stack and start executing code from there. Because this area right here is most likely already part of that buffer that was provided as part of the overflow attack. So you're basically providing the code as well as the jump instruction to that code to be executed on your behalf. It's that easy. And well, in many cases, the memory is randomized. So perhaps the attacker doesn't know exactly where to jump because it doesn't know exactly where its buffer is going to end up in memory. Doesn't matter. We have a solution for this as well. If we don't know exactly where to jump, that's okay. We just fill in as much as possible with a huge buffer in here. We take up all the memory, or as much as possible, and we fill it with do nothing instructions, which are also called NOPs, or no operations in assembly language. And at the very end, we put the actual malware code right here. So we don't know exactly where our code is going to end up, or where our code is supposed to jump to execute it. We just fill the memory with NOP instructions like these, and whenever we jump that code, you just have to hit some position inside of this NOP area. Doesn't matter where. When it hits a NOP instruction, it just moves on to the next, and then to the next, and keeps going until it reaches and executes our malicious code right here. And this, by the way, is called a NOP sled, because the code basically slides down through all these instructions, just ignoring them, just like a sled would go downhill until it reaches the executable code. That's the bottom of the hill. And by the way, if this happens inside of a stack, I believe it's obvious enough that we're going to call this a stack overflow. There are also heap overflows and other types of overflow, but for the exam at least, this should be enough right now. And well, at least now you know where the name of the website Stack Overflow comes from. Buffer overflow exploits can be very dangerous because they can either allow the attacker to inject their own code or to perform privilege escalation basically, or allow the attacker to read restricted areas from the memory, like regions that store secret keys and passwords and session IDs, for example. One thing to keep in mind is that if you're using a buffer overflow to perform privilege escalation, you can only escalate the privileges up to the privileges that the application is using to run, because you're basically tricking the application into running your own code, so your own code is going to run with the permissions that the application currently has. Now, you're not going to instantly become root, but you will become a valid user on that machine. Alright, so buffer overflows are bad, are dangerous. How do we prevent them from happening? Now, a first method would be, of course, write better code, write safer code. There are functions that are safer than others that perform boundary checking, especially in situations where you're copying information from one location to another. And secondly, we also have different programming languages that behave differently when they manage memory. For example, C or C++ are going to leave the memory management mostly into the programmer's hands. Now, on the other hand, we have higher level applications like .NET or Java or C# or any application written in .NET, for example, that have a more strict control over the input that you're providing. And their internal functions by default are safer. Now, the second one is called ASLR, that's address space layout randomization, which is basically just a way of confusing the attacker by randomly positioning those memory blocks like the stack, the heap, the libraries that get loaded in the memory all over the place, which makes it harder or even impossible for an attacker to determine at which address his or her malicious code is located. So they might not be able to execute it, even though they might be able to inject it. The stack canary is an interesting one. It's a very small integer value that is placed on the stack right before the return value of a function. Alright, so in our example right here, we could add a small value right here before the return address. Remember, we're writing this from right to left, and this one, let's say it's 42 right here. Now we monitor for this value. So if a buffer grows beyond its intended size and starts overwriting this value right here, now if we lose it, then we know that a buffer overflow has happened and that we're screwed. Alright, so that's a stack canary. That's just a value that you're monitoring in order to figure out if a stack overflow might be happening or not. Finally, we have DEP, that's Data Execution Prevention, which is available only on Windows, and it basically marks specific memory regions as non-executable. So in our example, we could tell the operating system that this entire space right here reserved for the stack is non-executable. So it doesn't matter if somebody manages to add their own code in here, it's never going to be executed because the operating system doesn't allow you to execute code from this location. So those are pretty much the main ways in which we can protect against buffer overflows. Of course, we start with input validation. Make sure you validate your inputs so that you won't even reach that situation where you have to worry about what would happen if a buffer overflow occurs. And of course, we have additional methods. For example, AMD has something similar to data execution prevention as well, but for now, this should be more than enough. Next up, we have race conditions. This is a design flaw, a coding flaw that allows a system to reach an inconsistent state simply because of the timing of its allowed operations. Now, this might not sound like much, but computers are designed to be predictable, deterministic, so having a sequence of operations that you cannot exactly predict what the outcome is going to be, well, that's really bad for computing. An example of this would be a situation where multiple threads attempt to write data at the same memory location at the same time. You cannot know for sure what the end result is going to be, which one is going to manage to write that data last, so which one is going to actually have a chance to store the data at that location. And the problem is that these race conditions can sometimes be exploited by attackers. A well-known example of such a vulnerability was called Dirty Cow. Somewhere back in 2016 it was identified. It's a privilege escalation vulnerability that can allow any application or malicious code to gain root-level access and completely hijack the device. How scary is this? And the name comes from the copy-on-write mechanism. You can look it up if you want to, but very badly implemented. So programs can set up a race condition to modify what should be a read-only, root-owned executable. So basically, a non-root user can change root-owned executable files on any machine. So that's the definition of privilege escalation. What's even worse is that sometimes these vulnerabilities end up completely unnoticed. So this one was actually present in the Linux kernel since 2007, and most likely it affected Android devices as well, because they're also based on the Linux kernel. Now, a specifically interesting and even commonly encountered vulnerability that relies on a race condition is the time of check, time of use vulnerability, which is abbreviated like this. And it happens when programs try to modify a resource or a memory address, but they check that memory address and then modify it in two different distinct operations. Why does this matter? Well, let me give you an example. So let's assume that we have two ATMs, right? ATM 1 here and ATM 2 right here. And let's draw a timeline right here in the middle. So this axis here is going to be time. And we also have a bank account with $100. Now let's assume we have two people with two credit cards that point to the same bank account, and they both want to withdraw that $100 at the same time. This is one scenario that could happen. The first ATM right here is going to check how much money is inside that account, and it's going to receive an answer that there are $100 available. Immediately after, the second ATM asks for the same thing. And of course, it's going to receive a positive answer. The account has $100. Now, the first ATM tries to withdraw the $100 that it was told that is available inside of the account. And the second ATM was also told that there are $100 available, so it's also going to try to withdraw that same amount. The end result? Well, we might end up with a bank account that currently has minus $100. Now, with real-life banking, of course, there's no point in trying to do this, but in a badly designed software, this is a type of situation that can happen quite often and can lead to corrupted execution, to crashing programs, and also to vulnerabilities that can be exploited. And the problem here is actually the fact that we failed to connect these two operations, the check operations and the use operation. So when the first ATM checked the amount of dollars inside of that bank account, it should have also executed the withdrawal at the same time, or at least in the same atomic operation, so that the other check here would not be able to happen at the same time and maybe misrepresent the state of the bank account to a different ATM at the bottom. So what's the solution for race conditions and time of check, time of use vulnerabilities like this? Well, design your code properly so you don't reach this situation. You can implement locks or mutexes or semaphores or any kind of locking mechanism whenever you want to check a resource before changing it, just to make sure that somebody else in the same time frame is not going to access it and be presented with a false representation of the state of the resource. And what I mean by somebody else, it's probably going to be another thread, another process, maybe another user trying to access the same resource. Another situation where a race condition exploit can happen is if an application uses a cache file, ideally located on the user's device, and uses that cache to store a temporary file or a temporary value for future use. Now, if the user or an attacker manages to change that value between the time that the value is stored in the cache and the time the value is used from the cache, this is exactly the type of race condition exploit that we're talking about. So the solution is to try to define atomic operations in your code. Operations that either execute entirely or not at all. In other words, don't program sequential independent operations when they could have been done together. Another one on the list of coding vulnerabilities is improper error handling. Now, before we talk about what's proper and what's improper about error handling, please make sure that you do handle errors in your applications. Don't just let the application crash into an unknown state. Make sure you catch those errors beforehand and you have some piece of code that handles that specific situation. Catching errors is called exception handling, and it is done using special code that is executed when a specific error situation or condition is detected. That's the code where you decide what you're about to do next instead of just crashing the application. And since of course you cannot just prepare for any kind of possible crash scenario that might cause your application harm, there's also a way to define in most programming languages sort of a catch-all exception. So if it doesn't match any of the known or expected conditions for errors, we also have a generic code that's going to handle any other type of condition that can lead to an application crash. So bottom line here, try to fail gracefully. Right? Don't just let the application crash, handle that situation using your own code. The point is that crashing an application is always very unpredictable and can leave your application in a very insecure state, which is very bad for cybersecurity. Also part of the exception handling code, make sure you deallocate memory when the exception occurs. Don't leave important data in memory when you don't know exactly in which state your application might end up. Also, don't provide just to anyone, to any user, things like debug information. Don't fall back to default configurations or to default pages. Don't provide stack traces or the full SQL statement that caused the error. Don't provide more information to a potential attacker than they should be aware of. It might be irrelevant information for a normal user, but it might be a gold mine for an attacker who just found out more about the backend of your application. And I know I've said this before a number of times, don't provide detailed authentication error details. So if it's just the username that's bad, don't tell this to the user. If it's just a password, don't tell this to the user. Just tell him authentication failed. That's it. Don't provide more information. The more information you provide, you're basically telling an attacker, you did not attack me right. This is what I expected. You don't want to do this. Now here's an example here of badly managed errors. So for example, in this field right here, if I add something like user ID 2, right, and press enter, well, I'm going to get some information about that user ID. But if I try to do a slightly easy SQL injection attempt in here and I click submit, the end result is that I'm going to be shown the exact error generated by the database engine in this site. So at the very least, I just found out that the backend is actually a MariaDB server. There you have it. We did not know this a couple of seconds ago. Why would you tell this to any average user that would access your website? This is not relevant information for them. I'm sure you can remember a lot of websites where you accidentally mistyped some information and you ended up seeing some part of the SQL statement that generated that error. That's also part of badly managed input validation and also badly managed error handling as well. Okay, moving on to other software design issues that can lead to vulnerabilities. One of them being using insecure components. Well, developers don't like to reinvent the wheel. So on each new software project, on each new feature, well, we're going to look for somebody else who has invented the wheel before us. So we're going to reuse some libraries, some code that wasn't perhaps thoroughly analyzed for vulnerabilities. So careful when reusing code. And this also applies to third-party libraries and their vulnerabilities as well. SDKs or software development kits that are sometimes used by developers most often include some sample code, some sample applications that are used as code skeletons for the future application. Most likely these samples were not designed with security in mind, so any problems, any vulnerabilities that were in the sample code from the very beginning might end up in the final code at the end of the project. And even if you're thinking, well, I'm not a programmer, I don't need to worry about this. Well, even if you're just managing a website, that website is probably going to be using something like Joomla or WordPress, and you're going to be using themes and plugins that you download from the internet. Well, that's actual code that you're reusing and that might have certain vulnerabilities. So if you must use third-party code, think about some mitigating control. For example, like a web application firewall that can put in front of your web servers and can protect you from well-known web-oriented attacks. Secondly, we have insufficient logging and monitoring, and a lot of security incidents are detected and eventually avoided thanks to the magic of logging and recording all the events that happened, when it happened, who was responsible, what was affected. So make sure you log the behavior of your applications, but be careful not to log too much information so that it becomes unmanageable. At the very least, design your logging mechanism to store at least information regarding, successful operations, failed operations. Make sure you don't expose any sensitive information in your logs. Make sure you store the input validation errors in your log so that later on you can identify any attempts of breaching the security of your application. Any abnormal events like attempts to tamper with file integrity or to access application regions that are normally inaccessible for regular users. Any attempts to connect with invalid session IDs that can suggest that somebody's attempting to perform some session stealing, cookie stealing, session hijacking. Any admin function usage. Make sure you log everything that is recorded as being performed by an admin, just to make sure that there was an actual admin running those commands and not somebody who escalated their privileges or impersonated an admin. And I don't think I have to mention this, but restrict access to those logs. Make sure that regular users cannot access those logs, and not to mention make sure that they are not able to change or write or delete those logs. And generally, don't ignore logging. It might sound like a trivial habit, the type of work that nobody wants to do, but having continuous monitoring is very useful, especially when your company doesn't really have a strong security posture. Now, the chances are that when you get compromised, you will find out after the incident has happened. And if you don't have the proper monitoring tools in place, you might not even know how it happened and what you need to do in the future to avoid finding yourself in the same situation, to avoid being breached in the future as well. Then we have weak or default configuration, and the main idea here is that regardless of how secure the code of an application is, if an admin or a privileged user decides accidentally to expose some sensitive information, well, that's a vulnerability that was introduced from the application's configuration. So somebody misconfigured the permissions in that application and accidentally exposed something that shouldn't have been visible. Very important, don't forget about default configurations like default configs in Wi-Fi devices, in IoT devices, in networking devices, and I don't know, your home wireless router, for example. They all have default accounts with default configurations, which are well known, and there are automated tools out there that search for these exposed admin interfaces exposed to the internet, and they just brute force try to connect using those default credentials, and more often than not they succeed because people forget about those. So make sure you change your default configuration and your default accounts, and even renaming the admin accounts is a well-known practice for just obfuscating some sensitive information. Try to make the attacker's life a bit harder. If every admin user all over the world would be called admin, then the attacker's job would be only to crack the password. But what if the attacker doesn't even know what is the name of the admin account? Why not use this? Finally, broken authentication. This one refers to an application that performs authentication and authorization for the user accounts that it has, but it does them badly. And this can be due to a number of faults. Like, for example, the application can accept very weak passwords. You allow your users to use very weak passwords. Or it has a very weak password reset mechanism. A badly implemented password reset would be, for example, to ask the user to provide the email address where the new reset link or even the new password is to be sent. Now, of course, an attacker would easily be able to reset anybody's password using a mechanism like this. Or even a system that resets all passwords to the same default one. Don't laugh, You can find this in real life and it happens. Also, it might happen that the application can expose some sensitive session information, like unique session IDs, credentials, or authentication tokens, either because they're not encrypted or they are hard-coded in the application, or exposed somewhere like in the URL of the password reset link. Another situation is when the application stores all these credentials in clear text, which exposes them all if the system is accidentally compromised. Now, for a full list of best practices, have a look over this authentication cheat sheet hosted by OWASP. It's going to provide you with a lot of guidance and cover most, if not all, the possible scenarios when the authentication implementation might be broken and vulnerable to outside compromise. Now, I would like to mention one more here, last but not least, dereferencing. Now, dereferencing is the operation of accessing the data stored at a specific memory address. Perhaps that address is stored in a pointer, and well, the operation of accessing that information is called dereferencing that pointer. Now, there's a situation called null pointer exception when an application tries to read a null memory address, for example, in an empty, not yet allocated pointer. This can result in a program crash. Most of the time it's going to be a program crash, but this can happen accidentally due to a bug in the code, which can be easily fixed by adding some sort of logic, to check the pointer before trying to access the contents of that memory address, or it can happen as a result of a code injection like a buffer overflow. In either case, it's going to warrant investigation because you're either going to crash your application or you're going to get breached. And neither situation is desirable. Alright, that's it for today. We're going to leave the rest of the attacks and the mitigation methods for the next episode. And trust me, we have so much still to cover. Don't forget to like and subscribe if you found this useful. That's exactly what keeps me going and the least you can do to help me keep motivated to provide you with content like this. Thank you for watching and see you next time.